All right, I think I am set up to do this. Do you guys have any last minute questions on any of the content before we start on the practice exam? Oh, Sarah, yes, please share. She says she has a good way of remembering when delta H, delta G, and delta S are positive or negative. And that's actually sometimes I confuse myself. So I would love to hear it.
Okay, so the way that I looked at it is that, so for all of them, the positive one has more letters than the negative one. So non-spontaneous is positive and it has more letters than spontaneous. And endothermic has more letters than exothermic, so it's positive. And disorder has more letters than order, so it's also positive.
Oh, that's great. That's very simple and easy to remember. I like that. Thanks, Sarah. That's great. Well, anything else? Should we jump in? Okay, let's jump in then. So today's lecture is the practice exam because we have our exam today. And you may have already attempted it at least once, if not both times, but it's always instructive to go over it with me because you can kind of see how I approach the problems and so on and so forth. And sometimes you can kind of catch hints of how else I might ask that question on the test, which can be very helpful. So this practice exam has 25 questions, but the actual exam only has 20 because it has to be taken inside of a 90-minute period of time. So just a heads up, even though this one's a little bit longer. Here we go. As you'll notice, if you haven't noticed already, my exams follow basically the same order that the lectures do. So we're going to cover chapter 5 on reactions. And then after we cover a couple of problems from chapter 5 on reactions, we're going to jump into chapter 6 on mole and molecule and mass relationships. And then after we do chapter 6, we're going to jump into chapter 7 on enthalpy, entropy, collision theory, so on and so forth. So just kind of a heads up on that. If it's got 20 questions, you can expect just 6 or 7 questions from each chapter. So pretty short. Okay, so let's see this. Question 1. An aqueous solution of sodium carbonate is reacted with an aqueous solution of calcium chloride. Which of the following is a valid precipitation product for this reaction? And you guys might probably already know. Whoops. Here we go. But just to make sure that everybody's on the same page, we'll do this. And the first thing that I want you to notice is that, yes, I gave you the names. And so you have to remember what we learned from our last exam on how to get the molecules from the names, right? So we have sodium carbonate, Q, plus an aqueous solution of calcium chloride, AQ. And they're telling me that I'm going to have some sort of precipitation product. So something that's solid. So we have to predict what those are. And do not eyeball this. Don't just be like, I get sodium chloride and calcium carbonate. And then right? But I need you to pick these apart and look at the ions because your ion charges still have to cancel. And that's an important part of this. So sodium is group 1, so it's Na+. Carbonate, you guys memorized. It's CO3, and you have to memorize that it's a 2-. And calcium's in group 2, so you know it's calcium with a 2+. And then chloride is in group 7, so you know that it's a 1-. Does that make sense? So from here, you can predict that this formula for this is going to be Na2CO3 because you're going to need 2 sodiums to make that work. And here, you're going to need 2 chlorines, CaCl2. Okay, and then your products are going to be, if you'll remember, we take our outside ions because the positive with the negative, and the inside ions because the positive with the negative, right? And so when we predict our products, we're going to get the sodium with the chloride because it's +1 -1, I just get NaCl. And then the calcium with the carbonate because it's +2 -2, I just get one of each. So I get CaCO3. Just like that. And then I can go back and say, according to the rules that I memorized, and yes, you have to memorize them for the test, for solubility, which of these is the precipitate and why? Sarah says that calcium carbonate is the precipitate because it's not on the table of rules. Okay, so that is, that's right. So when you look at the table of the rules, that's the table of rules of things that are soluble. So if you're not on the table, then you can predict that it's not going to be soluble. So that's going to be the precipitation product. Does that make sense? Yeah, and the rules say that everything in group 1 is always soluble. All right, so this is the process that I really strongly recommend that you go through. Like, make sure that you pick apart your individual ions so that you know exactly what the reactants are, and then predict the products based on that. And yeah, hopefully this is not a surprise to you that I'm still going to be using names, even though it would be way more convenient for you if I used formulas. Okay, the following reaction may be classified as an oxidation reduction reaction. We want to know if so, like, what is it that makes it classified as an oxidation reduction reaction? What's reduced, what's oxidized, and why? So in order to answer this question, we have to assign oxidation numbers. And because these are all covalent compounds, we have to assign them following the rules for covalent compounds specifically, right? And that was the fact that, for instance, you have this order, like if there's a hydrogen, it has to be +1, and then everybody else gets what they get, right? So if there's a hydrogen here, I'm going to say that's +1. And since there are 6 hydrogens, that gives a total contribution of +6 for this side of the molecule, which means that since there are 2 carbons, then each carbon has to be what? -3, right? -3 times 2 is going to balance my +1 times 6, so that the overall sum of oxidation numbers is the charge, which is 0, because these are all neutral compounds. Good. What's the oxidation number on this oxygen? Erica's right. Perfect. It is 0 because it's elemental. It's all by itself. In fact, if the oxidation number on each of those oxygens was -2, you'd have to see a charge on the overall molecule of 4-, right? Because those would add up. Okay, in this compound, CO2, now I can say the charge on the oxygen, the oxidation number on the oxygen is -2. There's not a hydrogen or a fluorine, so I get to assign oxygen. And since oxygen is -2 and there's 2 of them, what does carbon have to be in this molecule? Oh, you're on it, Sarah. Perfect. All right, and then for this water, hydrogen gets to be assigned first. It's +1, and if there's 2 of them, then that means the oxygen has to be -2. Perfect. Now, that's the hard part. Assigning oxidation numbers is the hard part. Next, you just have to look at what changed and then assign, okay, what was reduced and why. So what changed? The carbon and the oxygen. The carbon went from -3 to +4. Wow. And the oxygen went from 0, and in every case in the products, it's -2. So the oxygen became more negative and the carbon became more positive. All right, so then which of those was reduced? The oxygen was reduced because why? Is it because it gains or loses electrons? It must have gained electrons to become more negative. That's right. Because the oil rig, right? Oxidation is losing electrons and reduction is gaining electrons. So when I ask what's reduced, you know I'm looking for the thing that gains electrons. In fact, you can eliminate all the options that are losing electrons there. Okay, so that's question 2. All right, so let's do it again. Question 3 is asking you about the oxidizing agent, which again, the oxidizing agent is not the thing which is oxidized, it's the thing which helps something else be oxidized. So it would be the thing that got reduced, right? So let's make that a little bigger so we can see what we're doing. Oops. And in order to figure this out, it'll be easier if we can assign oxidation numbers. So we're going to come along and assign oxidation numbers. This is a little easier because these are ionic compounds, right? So the oxidation numbers for the ions is the same as the ion charge. So what's the charge on potassium here? And the charge on chlorine? Good, +1, -1. All right, the charge on silver here? +1. Okay, and then I can assign oxidation numbers for nitrate, but I'm actually not going to. I'm just gonna say, look, there's nitrate on either side. And so because there's a nitrate on either side, whatever those numbers are that I would assign, they're gonna be the same on either side. So I'm not gonna worry about it. I'm just not gonna assign it because it doesn't appear to have changed, if that makes sense. All right, but potassium here has what charge? +1, good. And the silver here has what charge? Good, and the chlorine here has what charge? -1. Okay, so now that we've assigned the oxidation numbers, that was the hard part, we look for what changed. So you guys tell me, what changed? Nothing changed. So nothing was oxidized or reduced. This isn't an oxidation reduction reaction. It's a precipitation reaction. Actually, you can see it right there. And because the charges don't change, it doesn't, okay, so there is none. A little bit of a trick question. I mean, is it a trick question if I tell you I'm gonna try to trick you? Is it still tricky? I haven't decided yet. Does that make sense to you guys? Okay. All right, next we've got a solution of potassium hydroxide mixed with a solution of magnesium iodide, and we want to know which of the following species is a spectator ion for the reaction. Oh, so many words, and they just are not as useful as a reaction, right? So let's write it down and draw it out. So we have potassium hydroxide plus magnesium iodide. Let's pick these apart and figure out what these actually are. Okay, so we're going to bring this down here. These are ionic compounds. The potassium ion looks like what? Oh, Sarah's got it, Erica's got it. It's K, and it has a charge of +1 because it's in group 1. And then you guys memorize hydroxide. It's the polyatomic ion. OH, it's got a charge of -1. Good. Excellent. All right, magnesium is in group 2. So it's going to have a charge of +2. Yeah, perfect. And then iodide is in group 7. So it's got a charge of -1. Okay. So when we put these together, we'll see we actually +1 -1, that's all right, KOH. Plus, and then we have, I've got to have 2 iodines, right, to make that work, MgI2. All right, and then we're going to make our products, and we're going to combine that first positive ion with that last negative ion, and then our internal ions here, right? So the K plus with I minus is just one of each. Great, good job, yeah, Ki. And then the magnesium with the hydroxide, because magnesium is +2 and hydroxide is just -1. I have to make sure that I got 2 of those, right? All right, what kind of reaction is this? It doesn't tell us. but I'm mixing two aqueous solutions, so it's probably either precipitation or acid base. And hopefully you guys can see it's not an acid base, right? Because I'm not mixing an H with an OH. Okay, so this is probably precipitation. So which of these would be the precipitate, if there would be one, if we're right about that? Yeah. Okay, so, oh, you know what? I don't have space here. Let me make some space. All right. So if we stick these together, our precipitation rules, solubility rules say that potassium, everything in group 1 is always soluble. So that's going to be, I know that's going to be aqueous. The iodide, all the halogens are almost always soluble, and magnesium's not an exception, so that'll be aqueous. And of course, potassium is still always soluble, but neither magnesium nor hydroxide are on that list. So this is going to be a solid. This is our complete molecular equation. So if we remove the things that aren't really reacting, those are the spectators, right? Then we'll get the net ionic equation. So what's the same? Actually, it might be easiest to look at what's different, right? Aqueous, 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 solid. This is different. So that's going to be in the product of my net ionic equation, right? And then what went to make that is also going to be in the product of my net ionic equation. So I can say what went to make that was the magnesium ion specifically, just that guy. Maybe I should. All right, was this magnesium ion? And the hydroxide ion here is that coming together that made it. So this is going to be my net ionic equation. So anything that's not in my net ionic equation is a spectator. So in that case, it's going to be this potassium, which is aqueous on both sides, and this iodide, which is aqueous on both sides. Those are going to be spectators. Clearly, I only included one. It would be rude for me to put both of those on there unless I let you choose both of those, because you can only pick one. So the potassium is it. Does that make sense? Okay, and this next one is also asking about net ionic equation. So instead of asking what the spectator is, it's saying what's the net ionic when I'm done. So let's look at this. Again, I'm describing this in words. We've got HCl, aqueous, plus lithium, lithium hydroxide, rude, aqueous, goes to form what? Okay, and just to pick this apart here, lithium is in group 1. So it's just going to be Li plus. And then again, you memorize hydroxide. That's atomic. That's just OH minus. And it can be instructive to pull that apart too. Just to be careful and precise, that's H plus and Cl minus, right? So again, if we mix the outsides and the insides, we're going to have, let's see, H plus the OH is going to make H2O, and that's going to be a liquid, plus LiCl, and lithium is in group 1, so that's always going to be soluble. That'll be aqueous. Okay, so Sarah notes something. She says, look, it's acid-base, and you know the acid-base always has a net ionic that says the H plus the OH minus goes to form the water. That's true, but if you forgot, then this is how we would get there, right? We would say aqueous, aqueous, liquid, aqueous. So the liquid is the thing that's different, right? So that's the thing that changed. So it's going to be in the net ionic equation. And then you'd say, what made that? Well, of course, it was the H plus ion combining with the OH minus ion that made that, right? So this is going to be your net ionic equation, right? Your H plus aqueous plus your hydroxide aqueous going to form your liquid water. this is what's in your net. So any one of these three species is fair for me to ask about, but of course I only included one, and there she is. Does that make sense to you guys? Okay. Ooh, this one looks fun. Does that look fun to you guys? Oxidation number of an ionic compound with a polyatomic ion in it. Is that not your idea of fun, Erica? It is work. It is work. Actually, it looks scary to me. Oxidation reduction, at least when I was a student, was really scary to me. Not nearly so much now, but it took a lot of practice. So I get you. All right, so this is both an ionic compound, right? Because there's your positively charged ion, your negatively charged ion. But then your negatively charged ion is a polyatomic, which is held together with covalent bonds. So we have to follow all the rules, right? Both the rules for the ion the ion charge is the oxidation number, and when you've got covalent bonds, you have to follow those rules, and so on and so forth. So some of these are going to be easier than others, but we'll start here with the calcium. Because it's an ion, it's pretty straightforward, just the ion charge for calcium. It's in group 2, so it's going to be +2. That's not so bad. All right, now we know that the SO4 altogether is -2. You memorize that, but if you forgot, then you would note that the calcium would have to balance out a -2. So the sum of just the sulfur and oxygens needs to be -2. Well, if you're following the rules for covalent compounds, you have to assign hydrogen first, but there's not one, and then you assign fluorine next, but there's not one, and then you assign oxygen. And what does oxygen get to be in that case? -2. Perfect. All right. But there's 4 of them, right? So we've got 4 times -2 is equal to -8, right? So if the thing overall here has a -2 charge, and this is contributing -8, that means that this sulfur must be canceling out all but 2 of them. So it's got to be a +6. Does that make sense? Right? Here we were just looking at the sulfur and the oxygen and aiming for -2, but we could look at the entire thing and say, look, I've got a +2 from the calcium. I'm going to add X from the sulfur, and then I'm going to subtract 2 times, or we could say add 4 times -2. I can do math, equal to the overall charge of 0. That's another way of doing it, right? And then you'd solve for X, and you'd see X is +6 right there. Yeah, whichever way makes the most sense to you, do that. It works. All right, and oh, nice conceptual question. I don't have to solve anything, that's nice. Which one of the following substances is produced during an acid-base or neutralization reaction? Right, Sarah already told us, if it's acid-base, it always looks like this. So you're always making water. There we go. And can't get away without balancing an equation. Surprised I didn't see one of those earlier. Okay. If we balance these using the smallest possible numbers, what is it going to be? All right, let me give you some room for coefficients. And I see 1 calcium here. Whoa, 3 calciums there. All right, I'm going to put a 3 in front here. So I've got 3 calciums on both sides, right? And then I'm going to skip the oxygens and the hydrogens because it feels like they're everywhere. So I'm just going to skip that for the moment. I'm going to look for phosphorus because there's only 2 places, right? 1 place here, 1 place there. And interestingly enough, it's not just phosphorus, but it's this whole phosphate group, PO4. I'm going to balance that entire phosphate group together. So if I balance the calcium and the phosphate groups together, then these three species, these two reactants in this product have to have this relationship. And now I'm just going to hope that the H2O falls into place, because if it doesn't, I'm in trouble. But remember, I'm not going to count these oxygens because I've already counted them here, right? So here what I have is 6 hydrogens, and hopefully you can see together, that means I also have 6 hydrogens here and 6 oxygens. All right, so 12 hydrogens and 6 oxygens, that does work. I'm gonna put a 6 there and it'll work. How do you guys feel about that? Is there a trick that any of you guys use to solve that one? Is there an easier way? Yeah, just following a couple of the guidelines that I think I told you. It is helpful to balance if you've got a whole polyatomic ion that doesn't change, keep it there. And if you see hydrogen in lots of different places, then just leave it till last. Leave it till last. Erica, do you do the little chart? Yeah. So some of you guys might find that it's really helpful, instead of eyeballing it, which is kind of what I do, to do a little chart. So you're going to say calcium, oxygen, hydrogen, and phosphorus on both sides. And you could start out by saying, look, I've got 1 calcium. It looked like I had 2, 6 oxygens, 5, like this, right? Yeah, if the chart helps you, that is great. There is nothing wrong with that. And just kind of showing you guys how that works for me. Oh, whoops, that would be, yeah, 4 times 2 is 8, yeah, okay, 9. And then that was 2 hydrogens, and then 2 phosphoruses. So this is how you would start it. And then you could start with the calciums and say, okay, I'm going to put a 3 in front of the calcium hydroxide so that they balance. And when you do that, you're going to come back here and say, okay, well, that changes my calcium hydrogen and my oxygen, right? Because you put a 3 in front of there too. And that's going to give you 3 calciums and then 6 to 10 oxygens, 6 at 12 hydrogens, and so on and so forth. And once your calciums look good, then you can balance your phosphoruses, and once your phosphoruses look good, then you can go back and balance your oxygen. So if you like the chart, that's great. It's a great way of putting it down on paper so you don't have to keep it in your head and get lost in the numbers there. That was kind of a complicated one. All right, here we are. Moles and molecules. Now, this is actually a pretty simple conversion, but as I've noted, the challenge isn't necessarily that it's simple, it's that there's a lot of things you can do from moles, and it's easy to do the wrong thing. And so I'm going to recommend, even though it's simple and you might not feel like you need to, I'm going to recommend that you use the roadmap, even on something as simple as this. So if you guys bring up the roadmap, and the roadmap is in your support materials page that I recommend you print off here. Edit, take a snapshot. Okay. I'll put this off to the side here. All right, so it gives me moles, and they're asking for molecules. And actually, if I ever come back to changing this roadmap, I would change this to say, instead of atoms, I would say particles of A, right? Because the smallest piece of a molecule is the smallest piece of a compound is gonna be a molecule and not an atom, right? So the smallest particles, depending on whether I'm talking about an element or a compound, would be atoms or molecules. So if you want to go from moles to molecules, this will help just remind you, hey, I've got moles, they want molecules. I have to use Avogadro's number. Like if I, just in case I wasn't sure, the roadmap will help me be sure. Yeah, I'm so glad you love it because it's really supposed to be helpful. Okay, so then we just plug this in here, right? We say 4.25 moles CCl4, and then we're going to follow the roadmap, and it says there's this many particles in every mole, so we want our moles to cancel, so we're going to put that on top, right? So we're going to say 6.022 times 10 raised to the 23rd molecules, no space, in every 1 mole CCl4. I should say CCl4. I could probably be smaller. Make my life easier. Okay. And then my moles cancel. If I plug that in, I should get the right answer. 4.25 times 6.022 times 10 to the 23 gives me, that's not helpful. Thank you, Windows calculator. Fix to exponent. There we go. 2.6 times 10 to the 24th. Yeah, if I counted those, I think I'd get lost in the zeros. But we're right there. Any questions on that one? Okay, next, what is the molar mass of magnesium hydroxide? Okay, so the molar mass is the mass of 1 mole, and I've just got to look this up on the periodic table, right? Simple? Well, you would think it would be simple, except that I didn't give you the dang formula like a jerk. Good. It's like I'm trying to emphasize that you have got to be able to come up with the formula yourself. Right? Because if you just look at magnesium and you just look up hydroxide and you add it together, you will be wrong. Right? Because you have to put it together with the right formula so that the ionic charges cancel. And you can't do that unless you're checking out to see what are the ionic charges of magnesium. And let's see, I've got this here. Magnesium's right there, it's in group 2, so it's got to be +2. And hydroxide you memorize, so it's going to be OH with a -1. Which means that when you put that together, the whole thing has to have 1 magnesium and 2 hydroxides. And if you didn't include 2 hydroxides, you're going to get the problem wrong. Okay. Magnesium. 24.31 right here. Excellent. And this means I have 2 oxygens and 2 hydrogens, right? So if I'm going over here and 2 oxygens each at 16, so plus 16, and 2 hydrogens each at 1, so I'm going to add 2. That's what I get, 58.31. All right, does that make sense? Now this says 58.32, but that's close enough. It's just a rounding error, right? Somebody's using a different table with very slightly different numbers. There's nothing else that's anywhere close to this, so I know that this is the right one. But yeah, you're gonna have to look out for that. It's not gonna be an obvious one-to-one. You have to watch your charges. Okay, next, what is the mass of this many moles of calcium nitrate? And again, this is a simple conversion, but just to make sure that you don't get tripped up by simple conversion, your roadmap says, look, if I give you moles of something and they're asking for, in this case, grams of something, it's just a little reminder, you're going to need the molar mass. Just use the molar mass to make that conversion. And don't accidentally use something else that you shouldn't, okay? All right, we were lucky this time they gave us the formula, so we just have to look it up here. Calcium's 40.08. And I have 2 nitrogens, so plus 2 times 14.01. And hopefully you see here, that's not 3 oxygens, that's not 5 oxygens, that is 6 oxygens. So 6 times 16. And that gives me a total molar mass of 164.01 or 164.1 grams per mole. Now don't jump the gun and say, oh, that's the answer. No, that's just the molar mass, and we have to do the conversion. But of course I put that there just for anybody who wasn't paying close attention, right? So you got to pay close attention. Okay, so 0.538 moles of calcium nitrate. And we have to use the molar mass, which is 164.1 grams per mole. So that's on the gram side, and we want that on top so the moles will cancel. Does that make sense? It is as simple as that. So multiply that by 0.538, and we get 88.27. Right? Now, here's the opposite. Calculate the number of moles in 1.43 grams Rb2C2O4. So here I'm given grams and I want moles, so it's telling me, hey, use the molar mass. And it doesn't tell you whether to multiply or divide. It's trusting you to use dimensional analysis to do that, to figure out which of those you need to do. All right, so Rb2C2O4, I don't know if you can see this clearly. Rubidium's number 37 here. It looks like it's 85.47, and I'm going to multiply that by 2 because there's 2 of them. Plus 12.01, that's carbon, times 2. Plus, I've got 4 oxygens, 16 times 4 gives me a total molar mass of 258.96. I'm just going to write that down. 258.96 grams per mole. Okay. RBO, I'm going to substitute that. Okay, so if I'm starting with 1.43 grams, RB, RBO, okay. I'm giving it a new name because I don't want to write Rb2C2O4. I'm too lazy for that. And hopefully now you can see I'm going to need to put that number on the bottom because the grams are going to need to go on the bottom to cancel. So every 1 mole of this compound has 258.96 grams of that. And now the grams will cancel. There we go. Grams cancel. I'm left with moles. That's what they asked for. Okay, so 1.43 divided by 258.96 gives me 0.00552. Wait, did they put that answer here? Did I do it right? I did do it right. It's this first one. You mean you still have to remember how to go back and forth from scientific notation to regular notation? You have to do that too? I am so rude. Hopefully you all recognize that. These are the same. Okay. But I wouldn't have you memorize it if I wasn't planning on using it. That's the key. Over and over and over again. All right. Excellent. Okay. Ooh. Mole to mole conversion. When the equation P4 plus H2 makes pH3 is balanced, we can tell that 2 moles of H2 will do what? So, and then our answers all have to do with moles of something else. So moles of one thing, H2, to moles of P4 or moles of pH3. Our roadmap tells us if we're going from moles of one thing to moles of something else, we need the coefficients of the balanced equation to make that conversion happen properly. Okay, so let's put this equation out there. Let's see if we can solve that. Okay, so got 4 phosphoruses here, so I'm going to need 4 phosphoruses here. And then that gives me 12 hydrogens in the product. So I'm going to need 12 hydrogens in the reactant. And that should be good. Everybody agree with that? There's like a 1 here. All right, so that is the correctly balanced equation. And of course, we can't solve this problem unless we have the coefficient of the balanced equation. That's those red numbers that I just stuck in there. All right, so we're going to relate H2 to both P4 and pH3. So I'm going to do 2 different conversions here to figure out what's going on here using those coefficients. And we'll start by saying, look, if I got 2.0 moles H2, and I'm reacting that with P4, then I can see that 1 mole of P4 will react with every 6 moles of H2. I'm going to put the moles of H2 on the bottom so they cancel. You guys can see that. And that tells me that 2 moles of H2, 2 times 1 divided by 6, gives me 1/3. 2/6 is 1/3. I should have seen that. So this is 1/3, or 0.33 moles of P4. Okay. So if I actually start with 2 of these instead of 6, then what I will actually react with is 0.33 moles of those. Okay. And then I'm going to do this again here and say, look, if I start with 2.0 moles of H2, and I am going to produce a certain amount of pH3, based on my coefficients, it looks like I've got 4 moles of pH3 on top and 6 moles of H2 on the bottom. And so my H2s will cancel here, and 2 times 4 divided by 6 gives me 1 1/3, or 1.33 moles of pH3. So 1.33. Okay, so then I look over here and say it's not going to react quite with 1 mole of P4. It's only going to react with 1/3 of a mole, so these are out. It definitely doesn't produce 4 moles of pH3. It only produces 1 1/3. It still reacts. It just doesn't react with as much of it. Okay, so this is the right answer. It produces 1.3 moles of pH3. Does that make sense? All right, that was just simple multi-mole conversions. I just had to do 2 of those for that problem. Oh, all right, here we are. This is the problem you guys have been waiting for all your lives. Am I right? Let me clear my working space. There's not a reaction. That's rude. Okay, so what I did here was I described a reaction, and so you have to pull that out and write it down, because the word problems with the descriptions aren't as helpful as having kind of the picture of what is happening with the reaction. So here we go. If 30.4 grams of CO2 can be produced in the reaction of C2H2 with oxygen to form CO2 and H2O, how many grams of H2O can be produced in the reaction? The reaction as described says I am reacting C2H2 with O2 to form, that means these are products, CO2 plus H2O. Everybody agree with that? That's what this statement is saying. So you have to kind of pick that out and write that down. And once you've done that, we can balance it, because we know we're going to need that. So I've got 2 carbons there. Going to need 2 carbons there, 2 hydrogens there, 2 hydrogens there. Gives me 5 oxygens. Ah, curses, everything's got to be multiplied by 2. 2 C2H2s gives me 4 CO2s and 2 H2Os. That gives me 2 plus 8, that's 10 oxygen, so I'm going to have 5 O2. So that's the balanced version of the equation that I pulled out of that. Everybody agree with that? Okay, so now they give us grams of CO2. In fact, I'm going to write this right up here. 30.4 grams. That was produced, and they're asking how many grams of H2O can be produced? Question mark. How many grams of that can be produced? Okay. So they gave us grams of one thing, and they want grams of something else. So if we go to our roadmap, they gave us grams of one thing, and they want grams of something else. And the roadmap tells us, oh, use the molar mass of that first thing to calculate moles, then use the coefficients to convert to the other thing, and then use the molar mass of the other thing to get back to grams. All right. We've got a plan. It's going to be a 3-step conversion. We can do this. Starting with what we are given, 30.4 grams CO2. We need the molar mass of CO2. Anybody know what that is? 1 carbon, 2 oxygens, 44 grams in a mole. Make sure that you remember that that goes on the bottom, so they'll cancel, right? Yeah, 44.01. I'm going to be lazy, and I'm just going to round to 44. It'll be okay. All right. So this tells me if I use the molar mass, I should be able to get to moles of that thing, which I did. Awesome. And now it says I need to use the coefficients. So when they say coefficients, there's a lot of different coefficients here, but I specifically need the 2 coefficients that are referring to the thing I know and the thing I'm looking for. So here I can say, I want to put the H2O on top and the 4 moles of CO2 on the bottom, so the moles of CO2 cancel. Does that make sense? Yes. Okay, and Eric is already ahead of me. I don't think she appreciated me being sloppy on my molar masses. She says the molar mass of water is 18.016 grams per mole. Okay, here we go. I'm going to put that on the top. Moles cancel. And I'm left with grams of H2O, which is exactly what I should get, exactly what they asked for. So now I just have to plug it in. 30.4 divided by 44 times 2 divided by 4 times 18.016 is equal to 6.22 grams of water right here. Does that make sense? This was work, right? You had to discover what the reaction was, then you had to balance it, then you had to pull out your molar masses and set up the entire thing. This is just about as hard as it gets. Okay. Not difficult, but maybe I like your description. It's work. You can do it. This is basically the same thing. I'll be honest, there's not going to be 2 problems like this on the test. There's just going to be one, because, again, there's only so much time in the world. Here I'm giving you extra practice, because you know there's going to be something like this on the test. All right, but this one, at least I gave you the reaction to start with, right? You still have to balance it, but I did give it to you. All right, 2 irons. Gonna need 2 irons. 2 aluminums. I'm gonna need 2 aluminums. Okay, 1 here. 1 there. Okay. Elemental iron is produced according to this reaction. They're giving us 5.34 grams of iron 3 oxide. And we want to know, react with blah, blah, blah. This is Yes, it reacts with aluminum. We know that. Thank you. What is the theoretical yield of elemental iron? That's just a fancy way of saying how much iron can I expect to get, right? So they want to know how many grams. So it's basically, again, it's the same thing that we just did here, except that they used some extra fancy words here to see if it would confuse you. And they actually gave you the equation instead of making you invent that. But it's still I'm going from grams of one thing they gave me to grams of something else. So I'm going to follow basically the same path. Good. Okay. And Erica's on top of this, 5.34 grams, Fe2O3. And she says she's calculated that molar mass. I've got 2 irons, each at 55.85, and 3 oxygens, each at 16. And if I plug that in, I get every 1 mole of Fe2O3 weighs 159.7 grams. Right, and again, we just pulled those masses out of the periodic table. You guys are with me? Good. Okay. So I've done this first conversion and I am at moles of that thing, so perfect. So now I just need the coefficients. So what's going to go on top and what's going to go on bottom here? Things. Yes, David, things are going to go on top and on bottom. Which things exactly? Sorry, I was just rambling on and it occurred to me that I'm just doing all this for you and not making you guys tell me. 2 moles of Fe on the top and 1 mole of Fe2O3 on the bottom. I should be making you guys do these. All right, moles of Fe2O3 cancel, perfect. And this tells me if I use those coefficients, I should be left with moles of the other thing, and I am. So what do I do next? We want, the molar mass of iron, and we want the moles on the bottom. So 55.85 grams of Fe are in every 1 mole of Fe. Erica gave us that earlier, just on the periodic table. And when we do that, our moles of Fe cancel. We're left with grams of Fe. It'll be great. Okay. Just going to plug this in here exactly as written. 5.34 divided by 159.7, multiplied that by 2, multiplied that by 55.85, and it looks like I get 3.73 grams of Fe, which is right here. Just like that. Again, this is about as hard as it gets. And there'll only be one that makes you go the entire route there, I think. Any questions? Okay. Well, here's our last question on this chapter, chapter 6, and this is a theoretical yield, percentage yield question. So let's see, when NH3 is prepared from 28 grams nitrogen and excess hydrogen, the theoretical yield of the NH3 is 34 grams. When this reaction is carried out in the laboratory, only 20 grams is produced. What is the percentage yield? How do I set this up? Sarah, I think you're right, but hang on a second. So we need remember that the percentage is the percentage. Percentage is going to be the actual divided by the theoretical, right? And then you multiply that by 100%. So, but they gave us lots of numbers there. I don't have just 2 numbers. I have extra numbers. So this is just me being like, do you know which numbers you're supposed to use, right? I'm being a little rude. Okay, so, but 20 grams is produced. That's the actual yield because that was what was actually produced. And it tells you the theoretical yield is 34 grams. And so you can just plug that in. And then you can multiply the whole thing by the 100%. So that 28 grams is actually not necessary. If you wanted to, you could use the 28 grams and go through this entire process and convert to grams of NH3. And if you did that, you'd find that the theoretical yield was indeed 34 grams, and then you could plug it in. But you don't need to, because I told you that the theoretical yield was 34 grams. So I gave you extra information here just to see if you could kind of filter out what was useful information for this problem, right? Okay, perfect. All right, so here we are, chapter 7. It's got a little bit less math, a little bit more conceptual, which I don't know if that's better or worse. Probably depends on the student. But here we go. Collision theory of reactivity, which of these are correct? And Sarah says the last two. So yes, must collide, they have to come into contact, and they must interact in specific orientations. The third statement for collision theory says they have to have sufficient energy, and that's just not listed. I think these were maybe put there to distract you to see if maybe you would think that that's what that meant, but that's not exactly what they're saying. So those are the only two that are correct for this one. Any questions on that one? That's a good observation, David. David says he thinks of it as having everything to do with the particles themselves and not the reactions per se. Okay, yeah, because yeah, I can see that. Doesn't matter what kind of reaction it is, it's the particles themselves that are doing the work. Yeah. Okay, let's see here. Consider the reaction shown. 2 carbon monoxide molecules react with oxygen to form carbon dioxide. My delta H is negative 135.2 kilocalories. And I'm asking, I say this reaction is what? Because the sign of delta H is what? So the sign of delta H right here, it's right there, it's negative. So because the sign of delta H is negative, the reaction is exothermic. Right there. That's a nice question. Do you like a question like that on the test? Feels a lot easier than this guy, right? Gram to gram conversion. Oh. Okay. For the reaction given below, what quantity of heat will be produced if 90 grams of C3H8 are consumed in this reaction? Ooh. Okay, so this is kind of like what we were doing up here, right? Except that I've got energy and we never did that. So let's kind of plug this in. How is that going to work? Essentially what we're going to be doing is off-roading here. Okay, this is my roadmap and energy's not on there. I'm going to stick it on there and I'll show you where this little off-roading path goes. Okay, so this reaction as written tells us, if you're looking at the coefficients, it tells us that, for instance, 1 molecule of this reacts with 5 molecules of that, or that 1 molecule reacts with 3 molecules, right? But it also tells us that 1 molecule produces this much heat. So that's kind of like a coefficient, right? You could do a mole to heat conversion using that. So from moles, we're going to do off-roading. You can go to heat using, again, the coefficients of the balanced equation. So, but they actually started us with grams. So we're actually going to start from grams of the one thing, and I want heat, so I'm going to go from grams to the moles using the molar mass, and moles to the heat using the coefficients. It's going to be 2 steps just like that. So if we do that, here's our setup. We start with 90 grams C3H8. That's 3 carbons, each at about 12 grams per mole, and 8 hydrogens, each at 1. It gives us, what's the molar mass for C3H8? for that conversion. Yeah, 44. 44.1, okay, grams. C3H8, okay. So if we do that, then our grams cancel and we're left with moles, which is just what we wanted. And we know we can go from moles to heat just using those same coefficients that we did previously. So this tells me that I'm going to get 488 kcal from every 1 mole C3H8 that burns. And when I plug that in, I'll get my answer. So initially I've got 90, divide that by 44.1, multiply that by 488, and I get 996 right there. Perfect. That wasn't too bad. Okay, number 20. The following is a spontaneous process at 25 degrees Celsius. Choose the answer which best describes the thermodynamic changes at this temperature in the process given. So this is like that chart that I was having you fill out in the worksheet where you had to predict delta H and delta G and delta S, right, for each of these. So, okay, so DH, DG, DS. Okay, what do we know, if anything? Okay, Sarah says they're all negative, but we have to figure out how we get there. I believe you. But first of all, I told you it was spontaneous. So if you weren't paying attention, you would be really confused. You wouldn't be able to answer it, but it is spontaneous, which tells you that delta G is negative. Good. And just looking at this, Sarah is right. I'm going from 3 molecules to 2 molecules, and that's going towards more order. So delta S is negative because it's going towards more order. Okay, gotcha. So how do you know DH? Right, so DG equals DH minus TDS, right? Oh, hang on a second, Sylvia. We know it's going towards more order because I have a total of 3 molecules on the left-hand side, 2 of SO2 and 1 of O2, going to form 2 of SO3. So it's a more organized state because I have multiple pieces combining to form fewer pieces. Like a couple of fragments of a window spontaneously assembling to make a bigger window. That would be more order. That kind of makes sense. All right, good, yeah. All right, so you don't know that it's exothermic or DH is negative based on the temperature. You don't know that because you don't really know anything about this particular process or reaction with reference to this temperature, right? So the temperatures that would be considered high or low for a system just depends on the system that we're talking about. Like if I was talking about freezing water, the temperature threshold for that would be the melting point of water, which would be 0 degrees Celsius, right? Which would be kind of cold. But if I was talking about the temperature that's going to make it spontaneous to decompose rust into elemental iron, that's going to be hundreds of degrees Celsius. So instead we have to use this formula like we did, and we'll note that this is negative and that this is negative. And temperature is always positive. So positive times a negative is going to be a negative, and subtracting a negative is going to make everything more positive. So if everything's becoming more positive because of this piece, and yet the thing is still negative, the only way that could happen is if DH was also negative. Does that make sense? So that gives us that guy right there. Good. All right. Which of the following energy diagrams represents a slow reaction with a large negative free energy change? I'm going to zoom out here because I can't see them all. Okay, slow with a large negative, it's this one. So the distance between the first line and the last line, right? This dip here shows a large negative change. This is a small positive change. This is a large positive change. This is also a large negative change, and this is a small negative change. So these two both show a large negative free energy change. But the height of the hump here is what makes this one say it's showing that it would be slow, and this would be faster because it has a small hump here. Does that make sense? So that activation energy, that has to do with the speed, and because that activation energy is so high, it's going to be slower. Okay, all right, we can zoom back in here. Which statement best describes the way a catalyst works? Catalysts make everything go faster. And so the way they're going to do that, oh, hang on a second. Why wouldn't, and Nicole's asking, you're talking about why this wouldn't be it? So this would definitely be slow because it has a large activation energy, but it has a very small free energy change there. As opposed to this one has a really big jump down. Good question. Okay. All right, so it's going to decrease the value of the activation energy. It makes that big hump smaller, so it makes it easier to go over the hump, makes it faster. Good. All right. I told you there'd be a question like this on here, right? You just have to come up with the equilibrium expression. And it's not necessarily super hard. I mean, the formula is pretty straightforward. It's reactants over, no, it's products over reactants raised to the exponents. But I'll be honest, it's really easy to get lost in the brackets and the exponents, so the lack of them. It starts to all kind of blend together in a minute, if at least for me it does. So just to narrow it down, I know products have to be on top and reactants have to be on the bottom. So I can eliminate this guy and this guy, right? And then here I know that, for instance, my NO has to be squared. So I can eliminate that guy. So NO squared times BR2 on the top, good. And then I need the NOBR squared on the bottom, which it looks like it is here. So it's going to be that one. Does that make sense? And it's really just kind of easy to get lost in them because they all kind of look the same. So use the process of elimination to simplify your life. It's my recommendation on that. Okay, so just conceptually, the position of the equilibrium for a system where K is equal to 4.6 times 10 to the negative third can be described as being favored to what? And the concentration of products is relatively what? Okay, so the left or the right, reactants is obviously to the left, products is the right. Okay, that's a weird way of describing it, but okay. All right, so remember that the K expression is always products raised to their coefficients divided by reactants raised to their coefficients too, right? And we did mention that if it was less than 1, then reactants would be favored. But this, just to kind of help show why that would be in this case, we see that the K here is 4.6 times 10 to the negative 3, or the K here is 0.0046, right? In this case. All right. So that means that we can convert this to a fraction. Maybe I can do it here. 0.0046. Can I do that to a fraction? Screw it. Okay, I can do this. So this is the 10th place, 100th place, 1000th place, 10,000th place. So this is the same as saying 46 10,000ths. Does that make sense? It's 0.0046 is the same as saying 46 10,000ths. Everybody agree with that conversion that I just did? Okay, so if the K, which is the products over the reactants, is equal to 46 10,000ths, it's saying that for every 46 products that I have in the pot, I have 10,000 reactants in the pot. And hopefully you can see by that, that means that there's definitely a lot more reactants. So the concentration of products is relatively small, and you're favored to the left because you're favored to the reactants. So it's the left and small. So really, if you're less than 1, then reactants are favored, and if you're greater than 1, products are favored. But it doesn't hurt you to actually like look at that number, because then I think it makes it a little clearer there. Okay, changing pressure does what? So this is a Le Chatelier's question, and I've got 2 moles of NO2 gas forming 1 mole of N2O4 gas. And it says increasing the pressure will cause the equilibrium to do what? What do you think? It's going to shift to the right towards products. Why? That's right. Gas molecules take up space and exert pressure. So if you increase the pressure, it says I'm going to offset that change by trying to decrease the pressure. And I can decrease the pressure by just creating fewer gas molecules in this space. So you go from 2 gas molecules to half as many gas molecules, and the pressure will go back down. Any questions on that one? Let's see how we did. Yay, we got 25 out of 25. Okay. That's all I've got for you today. Again, we're ending early so that you have time to go take your test. Normally, we would be taking this test in class, so I don't want to take up too much of your extra time, because I know you guys actually do need to set aside time to take it. So again, you've got 90 minutes. Please use your roadmap. Take your time to just go slow and steady, careful. Don't second guess yourself, but be careful and precise. And I'll let you go if you don't have any more questions.